Good morning. Today we're going to be looking at transformations of functions. Today should be a pretty easy one, a little bit of review, a little bit of new stuff, but let's get started with the classroom creed. Remember, you want to pass the class, you got to say the creed. It'll be extra credit on a test or something. Today is a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it's worth it every time. All right, let's get started with transformations of functions. Hopefully, the first little one or two is going to look super familiar, and you're going to be like, oh, that's easy. I got that. I can do that in my sleep. So, first thing we're going to look at, vertical shift. Take a function, move it up and down, right? Not that crazy. Not that crazy of an idea. Oh, sorry about that. Close. So we're going to look at the formula, y equals f of x plus c. A real generic formula that's just saying, hey, I'm taking any function, any set of numbers, funneled through a system, some equation that spits out another set of numbers, right? And I'm just going to add one constant number to it and see what happens. So if you add one constant number to that set, let's just see. So use the graph of the parent function. If you need a little reminder, that's called the parent function. Any function with no constants, nothing extra on it, always called the parent. Use the graph of the parent to sketch the graph of each function. So what I'm going to do is I'm going to sketch the parent first. I'm going to do this first one nice and neat. 0, 0, 1, 1, 2, 4, probably 3, 9. If you're thinking about squaring a number. So there is the parent function, nice and neat. I might not do it so nice and neat every single time, but there you go. That's the parent parabola. And right here, because we've got a plus 3 on the outside, it's not inside, it's not attached to or underneath the parent function. So the thing the function is doing is squaring, right? This is outside of the squaring. This is not included in the squaring process. So because it's outside, that makes it a vertical shift up 3. And I always just label it like that for my brain. Now, if you want to write it out in words, that's even better. You could write vertical shift up 3. If you want to plot a couple points, if you want to think in your brain, okay, 0, 0, 0 squared is 0, plus 3 is 3, you're welcome to do that. But what I do now is I just plot the vertex up 3. I go 1, up 2, up 3, and then I just redraw the graph. Boom. And that's really it. I'll label them. This will be the parent function, so we'll call this f of x. And then what did they call the function in this problem? They called it g of x, is the red function. So g of x. And if you want me to write those out, that's x squared plus 3. And f of x is green, and it is the parent x squared. Vertical shift. So you could imagine, if there was a negative number, what would probably happen to that vertical shift? Probably go down instead. I'll let you try that on your own, but I could give you a little heads up. If I were going to do it on the same graph, which I guess I could have put it all in one, probably start right here and do about the same thing. So you don't have to do them on the same graph. When I post the notes, I'll do them on separate graphs and label them real well. But if you're going to try it on your own, there's maybe a hint to do that. Okay, that's vertical shift. Hopefully that's not too wild. Hopefully you've seen that before. Let's get started now, though, on horizontal shifts, which are a little more complicated. It's kind of reversed, which tricks your brain, and it's inside of the function. So you have to be able to identify types of functions and how it will actually apply to the shift itself. So this one looks different, right? Like we were saying before, the function itself is x squared, right? That's the parent function. So right now the shift that's happening is inside of that function. The shift that's happening is like attached or close to the x. It's not on the outside of the function. It's actually the function is going to be affecting this shift, right? This squared will affect the shift of 4. So that's how to recognize a horizontal shift. A lot of ways people think about it is it's on the inside. It's not always perfect, but it's real good to look at it. And it might be inside of square roots. It might be inside of parentheses. It might be inside of absolute values. But if you see this x plus 4 or minus inside of your random function, then you might know that it's a horizontal shift. So let's go look at the definition real quick. They do kind of try to trick you because we know that horizontal shifts or vertical shifts go up with positive and down with negative. And in your brain, you might think, okay, well, that means horizontal should go to the right if it's positive and left if it's negative. But that's not true. If we look at this graph, we can see that the negative sign shifts it that way and the positive sign shifts it that way. So it's like opposite of what your intuition might be. So it's good to know. Not that hard to apply, but pretty good to know. So when I do this box thing, I'm going to go ahead and say, I know that's left. I'm going to trick my brain into going left instead of right. And I know it's left 4. So let's see, that's the exact same parent function, right? I'm not going to do all the dots this time as perfect. Hopefully that's pretty darn close though. And then, okay, so that's my parent function. You call that parent function what? F of x equals x squared. And then what is this shift that we just said to do? It's inside the parentheses. It's getting affected by the function x squared. So because it's getting affected by the function, it's a horizontal shift. And because it's positive, it's going to the left 1 arrow, 2 arrows, 3 arrows, 4 arrows. Put my vertex there and draw my new function. Parabola shifted over. Questions? It's not too crazy. We're going to keep going. So you can imagine if you had a negative sign, we could do the same thing as we did last time. If you have this negative sign, it's probably going to go to the right 2. So then I could give you that little hint right there. Maybe I would start right there if I was going to do it. All right. Let's see what else happens, because this is where it starts to get crazy. Oh, no. We get to do, they give us an example to do both of them in the same one. So you're more than welcome and able to do 2 slides on the same thing. So if we take the first transformation, it's an up 4, right? If you want to write out the words, it's a vertical shift of 4 to the parent function f of x. And then the second transformation, this green transformation, looks like it's going to the right 3. A horizontal shift to the right 3. So I'm going to draw my parent function, which it looks like my parent function. They called this f of x, so I'm going to call my parent function, let's do p for parent. P of x equals the square root of x. That function kind of looks like half of a sideways parabola, right? Because it's like the inverse of the x squared, but we've got to make it a function, so we cut out the bottom half. And what we're going to do is we're going to go over 3. So in the green, 1, 2, 3. Over 3, but then I got to go up 4, right? 1, 2, 3, 4. Boop. And then I'm just going to draw my new function shifted. Not that crazy. Cool? Cool. Let's look at a quick reflection. And then we'll get to these stretches and these compressions and see a little bit more complicated. But hopefully these first 4 are pretty standard and you're able to do them with not too much difficulty. So let's look at these reflections. So it's the same type of thing. If we are looking at something that's happening inside of the function or attached right next to that x, or so let's say your function is x squared. Oh, like this perfect example. So your function is x squared, right? But that squared isn't, because of PEMDAS, that squared isn't touching that negative, right? That squared is only affecting that x. No matter what that x is, this is a negative number. This is kind of like rewriting it as negative x squared, right? That exponent is only touching that x because of PEMDAS. So technically this negative sign is kind of outside of the function, right? It's not getting affected by the parent function, which means it's a vertical, because it's outside, just like the vertical shift is outside. A vertical reflection is outside of the function. So this is a vertical reflection, but the accurate way to say vertical reflection, your brain can think of it like it's reflecting vertically. Like you're looking down in a pool of water and you're looking at your reflection. It's a vertical reflection. But the way we say that is reflected across the x-axis. Okay? So I'm gonna draw a little red dotted line that we won't use, but this red dotted line is gonna remind me where I'm reflecting. Then I'm gonna draw my parent function, which is the same thing I've been using, x squared. And I'm gonna say, because that negative sign's on the outside or not being affected by the function, we're gonna reflect it across that red line, a reflection across the x-axis. We're pretending the x-axis is a mirror. If you want to plot a couple points to make sure you're right, plot 1, 1, plug it into that system, and you'll probably get, if you plot, here, look, I'll show you. If you plot 1, 1, and then you plug it into that second function, chances are you're going to end up with 1, negative 1. Check it out, see if it's right. Make sure you got a good reflection. All right, second, we will do this one because this is the exact same situation, but across the y-axis, right? Because it's inside, parentheses, inside, but more specifically, it's being affected, the negative sign is being affected by the parent function. So that's because the negative sign gets affected by the parent function, it's technically inside of the graph. And so the original function probably looks something like this. There's our f of x, which is the square root of x. So that makes our reflection across the y-axis, if this is our y-axis, looks something like this. This is f, let's call it g. G of x equals the square root of negative x. Okay, so I guess I should have circled that and let us know a reflection across y-axis. And if we go up and we look at the definition of these functions, we can kind of see they give us that inside-outside look perfectly right here, right? That inside-outside look is the negative is inside for reflection across the y, like we just did, and outside of the function for reflection across the x. Cool? And there's two pretty examples right there of just random functions that they give us. So, there we go. Let's get to the fun stuff. Little wild, but not too hard. So we're going to look at stretching and shrinking. And we're going to try to use the processes that we just learned of like, okay, if it's outside, then it's a y. And if it's inside, then it's x. That's a good process for our brain to still use. And then we're also going to use the same process of if it's a big number or it makes sense that it should grow, it's going to be bigger than 1. And if it makes sense that it should shrink, it's going to be smaller than 1, like a fraction, right? Like if I'm going to give you a lot of money, it probably means it's bigger than 1. If I'm going to take some money, it means I'm cutting your money in half or in third or in a fourth. So that's kind of the way we're going to think about it. And then when we hop to x, just like horizontal shifting, you think it should go to the right, but it goes to the left. We're going to look at the same type of situation where if you think it should shrink, maybe it's going to grow. And it's kind of like the opposite. It's counterintuitive. Don't worry about all that. Let's just look at one example real quick. So this looks like it's outside, right? Because it's not being affected by that 2. Because this is technically 3 parentheses x squared. Same exact thing. Equals. So because it's outside, that means it's a bigger number. So we can go with our intuition and say this is probably going to stretch. This is going to be like I'm taking a rubber band and I'm stretching it vertically. Like if I had a rubber band and I started to stretch it vertically, then it would grow, right? It would get taller. So let's see. Parent function. And if I were going to take this parent function, grab it in 2 points and make it grow up, then it's going to get taller and probably a little bit skinnier. Just like that. And not only that, but we can define exactly how much skinnier it's going to get. It's going to get taller by a factor of c. So this is a vertical stretch by times 3. So that means every spot on this function is 3 times as tall. Not too crazy. So technically, I might have drawn it a little bad. If this is 1, 1, we should be sitting at 1, 3 now. Because each spot on that function got 3 times as tall. Same thing here, but we get shorter and squattier. It's like we're taking that Play-Doh and smushing it, compression. So this is a vertical compression by a factor of 3. Right? So we're going to take it and we're going to compress it. So if it says it should be 1, 1, now it's going to be 1, 1/3. It like shrunk by a factor of 3. So there's our parent function. Then we're going to take that parent function and just squish it down. So now we've got a shorter, squattier function. Right? So we'll call this h of x, and we'll call this f of x. All right? When I post the notes online, so if you go look at completed lecture notes, just for the sake of time, they're a lot more organized and a lot more written out. But so we can go kind of fast and talk about some of these concepts where I'm not going to write every single word I could, even though I would like to talk about each of them. So here's an example where you get to practice all 4 things. I don't want to do this for you. I want you to try this. I don't even want you to go back and look at the notes that I already posted. I want you to try doing this on your own, completely on your own, and then go check and see if you can do it right. Little hint for you to do it on your own. We've got some type here, some type here, something going on right here, and something going on. There's a bunch of them, huh? Right here. Those are all transformations happening to this parent function of x squared. The easiest one for me to go ahead and do first is probably this orange one. This one's the easiest. This one's the trickiest, I think, because you got to think about what that negative sign is doing. And then we've got a horizontal shift and a vertical stretch happening in that blue and green. And I'll let you try to practice on your own. All right. Let's keep going and do the exact same thing, but horizontally. Sometimes you can grab that function and just smush it up like an accordion or just stretch it out like an accordion. So let's see. But now it's going to be a little counterintuitive, right? So this says if your number is bigger than 1, it shrinks. But if it's smaller than 1, it stretches. So it, like you would think bigger than 1 growing. Nope. Counterintuitive, just like the horizontal shift. And also just like the horizontal shift, we're looking at the inside of parentheses or square root or absolute value. We're looking at what number multiplied by x is being affected by our function. So right here, boom, inside of those parentheses, right? So 2 is going to be affected by our function, just like x is affected by our function. So this is a horizontal, and then because it's bigger, you would think grow. Nope, horizontal compression. And it's going to get 1/2 as small, or 1/2 as big, really. So this one doesn't give us a great function because it's kind of more of a general sense. But we know from this function that it starts at 0 and it kind of makes a triangle that ends at 1 and 1, right? Well, we just said we're going to horizontally compress it like an accordion. So if one triangle made it all the way over, now guess how many triangles are going to make it? Exactly 2 triangles are going to make it. And then you could keep going if you want to go to 2, 3, 4, 2, 3, 4, 5, all the way over. But really what you need is that first one, and actually I'll go ahead and do this one nice and neat so you can kind of see. I'm going to go to -1 and draw the same 2 triangles. Boop, 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 boop. And then whatever happens after that, if you want to be perfect and draw 10 of them, feel free. I would love that. Okay, well this is kind of easy then, right? Now we've got because it's inside of the function, we've got a horizontal stretch by 1/2. So it's almost the exact same thing, but now instead of, I'm just going to copy and paste this. Now, instead of smushing it up, we're stretching it out, right? So it used to be 1 triangle, and watch this. Now it's a triangle goes all the way to the number 2. Just like that. Not too crazy. And it probably goes all the way to the number -2 as well. If I were to draw that out. And then you could keep going if you wanted to. Out to 4, out to 6, and so on. Horizontal stretches, horizontal compressions, vertical stretches, vertical compressions. All right. I think there's one more thing we really need to look at, and I think that's about even and odd functions, kind of like inverses, where we're just going to look at whether this function converts numbers into negatives or positives based on its exponents, right? So based on the exponents that this function has, is it going to change all of its numbers to negatives, positives, or it's just going to randomly shuffle them up because it's not all even and not all odd? But the formula for this, the formula to check in the mathematical proof of why something's even or odd is given right here. So it's even if you change all the x's for negative x's and it stays the same, even function. It's odd if you change all the x's to negative x's and it just pulls that negative straight out and it leaves it alone. So we'll see, because it's kind of confusing to look at that. But watch this. So what we're going to do is we're just going to change all of the x's for negative x's. No joke, we're literally just switching out every x we see for a negative x. Not too wild? Okay, and then we're going to do a little bit of algebra to kind of see what happens. So we know technically that negative x to the 5th is the same thing as negative x to the 5th, right? Absolutely. And negative x is the same thing as negative x. And this is kind of just some tricky math where we're going to pull that factor out. So we're going to pull out that factor of -1 and leave x to the 5th minus x. Well, holy smokes, look at that. We know x from up here. See this red box right there? We know x to the 5th plus x is technically just f of x, right? So that means that whole thing is technically just negative f of x. If we're seeing f of x as our red box right there, and the negative sign on the outside of it. So what that means is if we cut out that middleman, we got f of negative x is equal to negative f of x, and that's one of our identities up above. Pretty sure it's our identity for odd, but let's double check. Odd, f of negative x, spits the negative right outside the function. So does that make sense? Does it make sense that this is even or odd? Well, look at both of the exponents. Look at both the exponents and their whether they're even or odd. We've got an exponent of 5 and an exponent of 1, both odd. Kind of makes sense. But we're not going to just jump to that conclusion. Let's check another one. All right, so let's plug in g of negative x, see what happens. 1 minus negative x to the fourth. Oh, we know what happens to negative x to the fourth. Same thing that happens to negative x to the second, right? So g of negative x equals 1 minus x to the fourth. Holy smokes, that's the exact same function. And that's one of our definitions right there. If we cut out the middleman again, we're just left with g to the negative x equals g to the x. Therefore, this function is even. Does that make sense? Let's look at our x's and see. We've got an x to the fourth, and technically right here, don't we have an x to the 0? Are both of those even? Absolutely. Neither of those are going to take a x value that we've switched to a negative number and keep it negative, right? They're both going to convert it to positive. More specifically the 1 because there's no x value to convert, but with the x to the fourth, it's going to turn it into a positive. So let's look at one that has an even and an odd. And you can guess probably what's going to happen, but let's find out. You probably think, even and odd, it can't do both things. Well, let's see. So let's see, h to the negative x equals 2 times negative x, kind of weird, minus negative x squared. Okay, so one of them is going to keep its negative, and one of them is going to cancel its negative, right? So we're left with negative 2x, which is fine, minus x squared. Ooh. Well, that's not our original function. Like if I'm going to do this red box again, that's not the same thing. But what if I pull out a negative sign? I could try. Let's try to pull out a negative sign. Equals negative 2x plus x squared. Well, that's also not our original function. So h of x really doesn't relate to h of negative x in any special way. Well, that's not h of x. That is h of negative x because we changed the signs. So h of negative x doesn't really relate to h of x in any special way. Makes sense because the values or the odds and evens aren't consistent, right? We've got one odd and one even. So this is neither. Is that what it says? Neither up above? The phrasing of it. Neither even nor odd. Perfect. All right. I think there's one thing to point out that's kind of like, oh, why did you just eliminate negative signs all the time? And it's something that we kind of gloss over a lot of times. But if we're looking at x squared as a function, right? And we want to switch it to negative x squared. Well, then let's just pretend like we're switching x for negative x squared, right? Another way you can write negative x squared is the property of exponents, negative x times negative x, right? Well, we could go a step farther with that, and we could say that's actually technically equal to negative 1 times x times negative 1 times x, right? And then the properties of commutativity say we can move all of those around, go negative 1 times x. We're just moving around our multiplications. And what's negative 1 times negative 1? A positive 1, which is kind of goes away, and x times x is x squared. So there we see a little bit of proof why those even exponents kind of get rid of our negative. They don't get rid of it. They apply it. But when two negatives are multiplied by each other, they turn into a positive 1. So that's a little proof of why exponenting a negative gets you a positive number. And if you want the same proof for why a cubed one wouldn't work, well, by golly, then you're going to have 3 negative 1s and 3 x's. Whoa. 3 negative 1s and 3 x's. And we know that negative 1 times negative 1 times negative 1 actually gives us negative 1. So now we're left with a negative 1 x cubed, and that's why that negative sign popped right back up. Okay? That's just a little proof of what concept of what we were working on. All right, hopefully that helps a little bit. Make sure you're checking in with the lecture notes. Make sure if any of this isn't making sense, you're coming to office hours, you're really working on some of these practice problems, or you're making up your own practice problems, or you're identifying the things you do and don't know so you can try to learn them on your own. Because 1 hour in class really isn't enough for you to master this material. We really need to be working on it as much as we can and working on it efficiently so we're not just practicing problems that don't help us at all. All right, thanks for watching. I'll see you soon. I'll see you in class. Have a good day.